Welcome to Google Cloud AI Developer Relations Virtual Training. This is part 3 in our Junior Data Science series. My name is Andrew Furlich, and I'm a staff member at Google Cloud AI Developer Relations. In today's part, we're going to talk about alternative connectivity patterns and convolutional neural networks. Up to now, we've been talking about neural networks that either went deeper in layers or went wide. And what we mean by wide is having parallel convolutions. We're now going to talk about some historic state-of-the-art architectures from around the same time that explored alternative connectivity patterns, but were just as competitive in performance. So we'll cover DenseNet, which introduced the concept of feature reuse. Xception, which introduced a new architectural layout and a new type of factorization, and SENet, which introduced the concept of feature excitation. So DenseNet introduced the concept of a densely connected convolutional network, and it won the 2017 Best Paper Award. And it was based on this principle that the output from each residual block is connected to the input of every subsequent residual block. So this kind of extended the concept of identity link. And let me explain that in a little more detail. Prior to this, when you took the input, you did a matrix add to the output. And so, yeah, you were remembering something, but it was kind of diluted. Here, what happens in a DenseNet, instead of doing a matrix add, it does a concatenation. So there's no dilution of the feature maps. And they refer to that as feature reuse. So here's a pictorial representation of a dense group. And okay, let me back up. The replacing the matrix addition with a concatenation had the advantages of further alleviating the vanishing gradient problem going deeper in the layers. And it further reduced the computational complexity, that is the number of parameters with narrower feature maps. And we'll describe that subsequently in what's called a transition block. But here, when we look at a dense group, it's going to consist of one or more residual blocks. And what we've done is we pulled out that identity link operation, but you can see we've replaced it with a concat. And what that means here is think of the feature maps coming in here. And what we're going to do is we're going to concatenate them to the output of this residual block. And that means the input here consists not only of the output to this block, but the input to this block. And by concatenating those there, then the input to this one is not only the output from this block, but the output from this block and the input to that block. So here we'll look at a DenseNet residual block. It used what we call a B13 residual block pattern. If you're not familiar with this notation, it's becoming very common now in research papers. And this just denotes that it's a residual block, 2 convolutions. The first one is a 1x1, and the second one is a 3x3. Now, in case of the DenseNet residual block, it started off with a 1x1 that did a linear projection. That is, it did a dimensionality expansion, increasing the number of feature maps by 4 times. And if you remember from earlier discussions, when you use a 1x1 to increase the dimensionality, you are learning the best way to upsample the feature maps for your data set. Then the output of that went back into what you call a dimensionality restoration. That is, it restored back to the original number of feature maps, and it does a 3x3 convolution where you're going to do your feature learning, or you could call your feature extraction. Then the input here is concatenated to the output. So let's go ahead and show you a little code chunk that implements that. Another thing about DenseNet is it adopted the modern convention of using a pre-activation batch normalization, which we denote as batch norm, ReLU, or convolutional. Okay, and if you look over here, you can see our 2 convolutions, and they're now preceded by a batch norm and a ReLU. So the first convolution here is our one-by-one linear expansion. It's going to increase the number of feature maps by 4 times coming in. Then our 3 by 3 restores it. We call it a bottleneck convolution because we're reducing the number of feature maps. And then finally, the input is concatenated to the output of our 3 by 3 convolution. So let's look at a DenseNet from a macro architecture view. You have your STEM convolutional group, you have your classifier group, you have your learner in the middle, and the learner consisted of 4 dense groups. And if you notice between them is a transition block. Now, the purpose of the transition block was to control the size of the feature maps from sort of exploding. If you think about it, if I'm constantly concatenating the previous feature maps with the next set of feature maps, that's going to keep growing. And while it's not exponential growth, it is polynomial growth. Kind of think of it sort of as a trapezoid growth in size. And what the trans blocks do is after every dense group, they squash it back down. And that's the reference to the narrower feature maps. So here we'll look at a transition block. It consists of a one-by-one bottleneck convolution, which is going to reduce the number of output feature maps by they call a compression factor. Now that's a configurable attribute of the block, and therefore that's a meta parameter. And again, to remind you, when we do a one-by-one bottleneck convolution, we're learning the best way to downsample the data. Then that was followed by an average pooling layer that is a stride of 2. So that output is going to be half the height and half the width. So here we've reduced the number of feature maps, and then we reduced their size. So here I'm just showing a little code snippet for implementing this. So if we assume X is our input, we're going to want to find out the number of channels, or the number of feature maps, which is the last element in the shape of our tensor. We're going to times it by our compression, how much we're going to reduce it by. Then we're going to have our one-by-one bottleneck convolution. And notice here is that we don't have a ReLU. Instead, they used a linear activation. That is the default, and that's denoted by a BNLI conv. And then finally, we did our average pooling to reduce the size of those feature maps by an additional 75%. So here's an implementation of a dense group. So a dense group consists of a number of blocks, which you specify here. And then every block has the same number of filters and whether you're going to do compression or not. Now, if you recall, not every group ends with a transition block. Go back to this diagram. The very last one does not. And the reason it doesn't is because in the classifier at the bottleneck layer, you're going to do that aggressive downsampling with your global average pooling and then flatten it out to a 1D vector. Okay, so if we look at the code, we're just going to spin around for that many blocks. We're going to create or construct a dense block with the specified number of filters. And if we specify compression, then we'll add in the transition block. So the next one we're going to talk about is Xception, which is also known as Extreme Xception, and it's an architecture that was introduced by Francois Chollet of Google, and he's the creator of Carrots. And he introduced this in 2017 as a proposed and further improvement over the Xception v3 architecture. Now, if you remember me talking about the Xception series, I considered it to be an overly complex architecture. And since then, nobody has really gone to that level of complexity in the architecture anymore. And Xception was a way to reduce that complexity, though I still find Xception to be a little bit more complex than what you see in today's architectures. But in Xception, there were two major changes to the Xception v3 architecture. First, it reorganized the Xception architecture into three Inception-style residual groups called A, B, and C, which are referred to as the entry, middle, and exit flow. And here, the stem group is part of the entry, and the classifier is part of the exit. And then there was a further factorization of a convolution into what they referred to as a spatial separately convolution. Oh, God, I'm getting that wrong. Okay. The spatial separable convolution in Xception 3 was refactorized with a depthwise separable convolution, which I'll explain shortly. So here's the Xception architecture. You have your entry flow, your middle flow, and your exit flow. And you can see here in the entry flow, we include the stem convolutional group. And in the exit flow, we include the classifier group. And roughly, you could say between the entry and middle flow is where the feature learning occurs. And it's in the exit flow that the classification learning occurs. So here's a template for an Xception architecture. We're going to leave out all the layer information. So we're going to have three functions: our entry flow function, our middle flow function, and our exit flow function. And we're going to have as a embedded or a sub function, the stem inside the entry flow, the classifier inside the exit flow. So in the entry flow, we're going to instantiate the stem, construct it. And then it had three residual blocks referred to as a projection block, and they progressively increased in size. So there's a 128, a 256, and then a 728. The middle flow consisted of 8 residual blocks, all with the same number of filters, 728. And then the exit flow, for brevity, I've removed the code, and then finally the classifier with the specified number of classes. So let's look at the Xception entry flow. As I mentioned, it consists of 3 residual blocks, each starting with a linear projection. And you notice how they are increasing the number of filters. It's not quite double. The first time it's double, but the next time it's 3 times. So there's a progressive increase. The stem was a little bit different. So around this time, models stopped using that very coarse 7x7 stem and replaced it with a 5x5. A lot of researchers found that it was not only just computationally less, but it was had the same representational equivalence. And then later it was found that you could replace a 5x5 with a stack of 2 3x3s, still maintaining a representational equivalence, and that's what they adopted here. So here you have your stack of 2 3x3 convolutions. Now the first one was a strided convolution, which means it did feature pooling. And produced 32 filters. And then the next one outputted 64 filters. So you have this kind of strange different step where the first 3x3 is actually reducing the amount of information by feature pooling. And then the next one is actually doing a dimensionality expansion by doubling the number of feature maps. So the Xception entry flow residual block used the B33 style, which means that it was a stack of 2 3x3 convolutions, and then it's followed by a max pooling. And additionally, the identity link used a 1x1 strided convolution. So let's start up here. Our 2 3x3 convolutions are the normal convolutions are replaced with a depthwise separable convolution, which we'll discuss shortly. Okay, and then the output of that is reduced 75% in size by max pooling. Now our input, of course, to match that shape, when we do the add, we're going to do a one-by-one bottleneck convolution to reduce the size of the input feature maps by 75%, so that they match the shape of the output here, and we can do the matrix add. Okay, so this is a code block showing how to write that. So here we have our input and the number of filters that we're going to use in there. So here's our identity link. So it's going to start with we have our input, and we're going to then pass that input through our one-by-one bottleneck convolution. Our strides is 2, so that's going to reduce the size or the shape to 1/2 height, 1/2 width. And then we have our two 3x3 convolutions. Now in Keras, the separable conv2d layer is the depthwise convolution. You can see that at the time, it was still using the post-activation form of batch normalization, where batch norm follows after the convolution. Then here's our max pooling, which we reduced the output from these two stacked 3x3 convolutions to 1/2 the height, 1/2 the width. That's going to be the same shape here. And so we can do our matrix add of the input to the output. Now, the exception middle flow consisted of 8 residual blocks. Each of them had the same number of filters, 728. The middle style residual blocks use a stack of 3x3 convolutions. Each one of them is also a depthwise convolution. Notice these do not change the shape of the feature map, so the input is added directly to the output. Then the exception exit flow consisted of a single residual block using projection, followed by a regular convolution block, meaning there was no no identity link. Okay, so if we look at the residual block in the exit flow, it's kind of different. It's got two 3x3 convolutions, but they're not the same size. So the first one is the same from the middle block, it's the 728, but the next one increases it to 1024. And then we downsize the size of those feature maps by 1/2 the height, 1/2 the width. So we've increased the number of feature maps, but reduced their size. So along the identity link, we need a one-by-one bottleneck convolution that not only reduces the size 1/2 by 1/2, but also increases the number of feature maps to 1024 so that we can do the matrix add operation. Finally, there was the convolutional block, and that was simply a pair of 3x3s using the depthwise separable convolution, but each one increased the number of feature maps. So the first one was filters 1500 filters, and the second one 2048. And that's just like ResNet. If you recall in the ResNet, when you got to the bottleneck layer and you got to those final feature maps, there were 2048 of them. So let's talk about what a depthwise separable convolution is. So it's a convolution that it refactors a 2D kernel into two other 2D kernels, where the first one is a depthwise convolution and the second one is a pointwise convolution. So this kind of describe what's a depthwise convolution. Up to now, when we talked about a normal convolution, and this is our filter here, and we're going to move it across the feature map or our channel, we always did the matrix, the dot products, what we call the map mall, depthwise. We just went across all three at the same time, and we would generate one feature map per filter. Okay, well, in a depthwise, you don't specify the number of filters. Instead, you apply the kernel on a per channel basis. That is, you do the map mall only on that channel. So if you had 3 channels, you would produce 3 feature maps, 1 for each channel. That's a depthwise convolution. Then following that, you take those outputs and you're going to do a pointwise convolution. And this time your filter is a one by one a filter is going to be applied deepwise to generate a single feature map. So you've gone from producing, say, a large number of feature maps to just producing a single number of feature maps. So you have this substantial reduction in dimensionality. Okay, so let's now talk about the squeeze excitation network. That's an SENet. It came from the Chinese Academy of Science and others, and it was the winner of the 2017 ImageNet contest. And they introduced this idea of a squeeze excitation block that's placed inside a residual block between the convolutional layer output and then that matrix add with the identity link. And the authors refer to this novel architecture unit that allows networks to perform feature recalibration. And some of the benefits they stated by their ablation study included one that could be added to existing state-of-the-art architectures such as ResNet, ResNext, and Xception. And it added just a minimal increase in parameters while achieving higher accuracy results, as demonstrated by the fact that it won the 2017 contest. So here's a macro view of the SENet architecture. So in the learner block here, you have your one or more convolutional groups, but each group now has these SE links. And we'll dive a little deeper. So here is the residual group, okay, which is going to consist of one or more residual block, and each block has an SE link. Okay, so let's kind of look at what that really looks like. We're going to dive deep now. So here's our residual block. This is an existing residual block structure, say from a ResNet or a ResNext or an Xception. So you have the residual block part without the identity link. That is, we've removed the add out of here and we put it over here. And between this output and that add, we're now inserting another block, and we're going to call that an SE block. And that you could say is doing some post-processing on the output of the residual section before we do the add with the input. So here's an example of a residual block in an SENet. Okay, it uses in this case, we're using an example that uses the 3-3 form of residual block. Okay, so here we remember the input. Actually, this is not a B33. This is actually a bottleneck convolution. That should be a 1-3-1. Okay, so here's our dimensionality reduction doing a 1-by-1 bottleneck. I've sort of removed the remainder here. There would have been a 3-by-3 and then another 1-by-1 for a dimensionality restoration. And the output of that, instead of going straight to the matrix add, we pass it through the squeeze excite block. And we're also going to specify a ratio, how much we're going to squeeze it down by. And that's a configurable attribute of the network, and therefore that's a meta parameter. So here's an SE link. And this moment, my cat looks like it's joining us. The link consists of 3 layers. The first 2 layers perform what we call the squeeze operation. Okay. And so think of your input consisting of these feature maps. You can describe them as being height by width by the number of channels. And we're going to do global average pooling on them. That's going to really reduce them. That means every feature map is going to be reduced to a single pixel. Then we're going to even reduce it even more by putting that through a dense layer, but instead of having the number of nodes equal to the number of channels, we're going to further reduce it by our reduction ratio here. Then finally, we take that and we pass it through another dense layer where we say it does the excitation. It's going to expand it back out into a 1-by-1 by the original number of channels. And then finally, we're going to take the output of that and do a matrix multiply on the input. And that's referred to as the scale operation. So this is the squeeze, this is the excitation, and this is the scale. So let's go ahead and show the code for that. So here it is. We have that squeeze excite block. We remember the input. We're going to get the number of filters, number of channels or feature maps on the input. That's going to be our number of filters we want to remember. We're going to start our squeeze operation by doing a global average pooling. That gives us a 1D vector, or 1 element per feature map. We're then going to reshape that to be 1x1 feature maps, and then pass that through a dense layer that's going to compress it by our ratio here. And then we're going to do our dimensionality restoration, the excitation step. And then finally, the scale operation, where we multiply the output of this from the input. And that's the end of this part. Again, I thank you for watching. And there's an accompanying workshop that goes with it, which you can find at this link here. And again, thank you.